Okay, so we've covered quite a lot of topics in the mock. Two topics that I suppose aren't covered has been the bent beams and also the unsymmetric bending. So I think I just covered the unsymmetric bending as a bonus for anyone on YouTube. So I'm going to convert question 4 into question 6, and this is a bonus. So here we're going to get rid of our shearing force, and at the middle we'll change that shearing force into a bending moment. So I'm going to have X is pointing at me, X is pointing at me, Y is going left to right, Z is going upwards. Y and Z. And I'll put the bending moment going off in this direction here. Let's make it 3 kilonewtons meters. Is that reason? Make it 6 kilonewtons, and we'll put 30 degrees here. Right, so the things that we need to do then would be find second moment of areas for I, Y, Y, and I, Z, Z. So I suppose that'd be about 6 marks. Other things you would need to calculate MY and MZ. I don't know how many marks for that. Let's say 4 marks. Part C, we'll label these up. A, already got an A here. B, C, D. The bending stress at A, B, C, and D. And what else can we do in the formula sheet? That's it as far as the formula sheet goes. So let's leave it there. So we're probably I suppose about 10 marks for this. So it's not going to quite add up to my 25 marks, your bonus. Okay. Right, so for the I, YY and the IZZs, how would we do that? Well, we've done that previously in question 4 for IYY, so that's along this axis here. And the best method for that was to use the void technique. So IYY is going to be big B, big D to the power 3 over 12. Take away two lots of little b's and d's to the power 3 over 12. So we're imagining we've got these sections here, and we're going to take those two away, so that's going to be the red bit. And then the big B, big D is the entire cross section. Okay, so big B, we did this before, but do it again, is 60. 40 plus 30 is 70. Work in millimeters. The cross section for one of these is what? So that's 15 millimeters. 60 minus 15 divided by 2. So that's 22.5. And its height is 40. So that's 60 times 70 to the power 3. Take away 2 times 22.5 times 40 to the power 3. Divide that by 12. So that is 1.475 times 10 to the 6 millimeters to the power 4 divided by 1 times 10 to the 12. So 1.456, I could have done on my head, times 10 to the minus 6 meters. So now let's do IZZ. So you've got to imagine this thing now as a H-beam. And I don't think the void method helps me this time. So if it's a H-beam, actually, can you see with symmetric H-beam, what is the best method? It's not the void method. It's actually the classic split them up into sections method, because, and that's if it's symmetric, because the sections we want to split up is one here, one here, one here. Why is that? That's the centroid, that's the centroid, that's the centroid. We don't get any parallel axis theorem. So all we have to do is add up our BD's to the power 3. And two of them are the same, the outer ones. Hopefully that makes sense. So you need to imagine this thing moved 90 degrees onto its side. So I've got two of them. The width in this time is 15, and the depth this time is 60 to the power 3 over 12. And now for the middle section, plus the width is 40, there's only one middle section, and the depth is 15 divided by 12. So you've got 2 times 15 times 60 to the power 3, do the 12 later, plus 40 times 15 to the power 3, divided by 12. So that is 551.525 times 10 to the 3 millimeters to the power 4. So a lot easier to burn in this direction. And that divide by 1 to the 12. Should I do that, or let's do that? 0.55125 times 10 to the minus 6 meters to the power 4. Okay, so that's my first bit done. Second bit, really easy. We just imagine this to be a bit like a force, and we need to resolve it to its particular axis. So M y is going to be M cos 30. M z is going to be M sine 30. So my will be 6 times cos 30, in degrees, 5.196 2 for another number 2, and that's kilonewton meters. This one, I don't know, is that a big number? 6 times sine 30, that would be a nice number, won't it? 3 kilonewton meters. So, the bending stresses. Right, so when the arrow's pointing somewhere, you've got to imagine that you're using your right hand. So your right hand, and this is your arrow pointing, your right hand goes around it, and your thumb points in the same way as the arrow. And then your fingers tell you which way it's curling around. So we can see that it's curling out of the screen, back into the screen this way. When it's curling out of the screen, you imagine it to be pulling it apart, it's in tension. When it's going into the screen, you imagine it be squashing, it's in compression. So that's that. The next thing is that you then need to line up your moment vector with the axes vectors. So here, if we need to rotate this one down here, I'm still staying in the same quadrant. So I need to move this down by cos 30, and it will be pointing in the same direction as this axis here. So we can then say that nothing's been flipped in terms of direction. So this is basically happening. It's coming out along that axis and going into that axis. And again, if I try and move this to the closest, you move it, shift it to the closest axis here, and again this axis is pointing in the same ways as the z-axis, so that means that we're curling out and going in. Okay, now the only problem is that if that arrow was not in that quadrant, if that arrow was in this quadrant here, for example, it's fine for the z because you would be going in this direction, so you'd still have a positive z, but for your y you would be going downwards and you'd be pointing in the opposite direction of your axis. So if m was going off in this direction here, we'd make it go down, and we can use this value, but it would be a negative sign. So you basically see, try and shift your moment vector to the closest axis. If it's pointing the same direction, happy days, you just use positive numbers. If it's flipped direction, then you may have to put a minus sign in front of your numbers. So currently these numbers are valid. So the next thing is to work out what the bending stresses are. So we're going to use that, well, on the formula sheet here, it's given us that we've got this term here, but I'm going to not use it. Okay, I'm not going to use that expression. So we've got no direct stress, we've just got some bending stress. So we know that bending stresses take the form of M over I, Y, and we know that we've got two components, and one of them will be Z. Right. So for the MZ, sorry, for the MY, notice that the distance that you're looking to go away from that y-axis is going off in a Z direction. So your MY term, your MY term is related to the Z position. And the same thing is true for IYY. So IYY is along this axis here. So you use a Y here. So you've got your MY, your IY, they're in the same, going along the same axis, and this is going orthogonal to this axis. So here you have your MZ and your IZ, and that will be the stress going along in the x-axis. Okay, so I'm following convention everywhere. So for which one should we start off with? The easiest one to start off is D. So stress at D is going to be your MZ. I think that's the first one I got. Yeah, so that's 3. It's 3,000. And I is this one here, 1.476. That's 3,000. Okay, now the Y. Well, so what's the distance? So we are using this one here. So what's the distance from here up to the top? What's that Z distance? So it's 70, isn't it? 40 plus 30, 70 divided by 2 is 35. And here, let's worry about the sign in a minute. Here we're going to use, have I done that right? Oops. Yeah, MY. So, no, I haven't done that. I've mixed up my, ooh. I've done these the wrong way around, sorry. So that was this one here. So apologies. Okay, now let's do this one here. So that's the MZ. Puckering everything up. No, it's okay, MZ. Yeah, so previously I did my. So yeah, I've marked everything up. Let's go away, question 5. So let's start again. Okie dokie. So MZ, so we're going along this axis here, and our MZ is 3,000. Our IZ is along this axis here, so that's this one here, so that's the 0.55125. So we're along this axis here, and we've got to measure from here to here, and so that's going to be 30. I'm going to worry about size in a minute. Now let's do the MY. So that's along this axis here, so that's this number here. So 5.1962. We want to make that into 1,000. Okay. And then the distance from this axis up to here is 70 divided by 2, 35. And the IYY is this number here, 1.476. Now let's worry about our signs. So let's have a look what's happening here. So according to this axis here, for the 7-1, it's going in to the screen. So it's a negative. And for the for this axis here, it's coming out of the screen. Okay, so it's going to be a positive. Okay, and now we just need to repeat this for all the other angles. So let's go to C next. So for C, we are going to get the same values for your MY. So yeah, so the first one that we do is the along this axis here. What's the distance from here to here to get to the C point? That's 30. So you've got the same thing as above. Okay, and then to go from this axis up to C, from this axis up to C, what's that going to be? That's 35. So same thing as above. 51962 35 times 10 to the minus 3. Okay, so if I'm at this quadrant, what's happening in terms of what's going in and out of the screen. So for the first one, for the Z-axis, it's coming out of the screen. So for the first one, it'll be a positive. And for this axis here, well, it's also coming out of the screen, so the axis is going all the way along here. You know, we don't expect this axis to change its effect on anything along this line. So it is coming out of the screen, so it's also positive. Okay, and now for B. Let's work these numbers out, so I don't have to keep writing them down. It's going to be the same. So how large is that? Oh God. 163,265. One, two, three, 2, 6. 3, 2, 6, 5. 1, 2, 3, 2, 6, 1. Okay. So for B is here. So the first one I did was Z. So Z, so that means the first one, it's going in, so it's a compression. Here it's also be going in for B, so it's compression. And for A, so the first one is coming out, so it's in tension. And for the Y, it's going in all the way along. It's going in here, so that will be in compression. So you've got minus 163.265 minus 123.216 equals minus 286.48 megapascals. Here you've got 163.265, take away 123.216. My problem's quite easy because it's nice and symmetrical. So that it ends up as 40.49 megapascals. Positive is the same as this, but plus. And here we've got a negative, positive, so it'll be the same as this value, but minus. Okay, so hopefully I haven't confused you. I went slightly awry in the solution to get this idea of whether something's going to be in compression at a particular point. So you have a look where you're using your right hand and your thumb, and say to yourself, is that going into the page or is it coming out the page at that particular point? If it's going in, it's compression. If it's coming out, it's intention.